right, so we were talking about the 0, 1 property for quasi-regular mapping, so this theorem. So we either have that the determinant of the quasi-regular mapping is equal to 0 for almost every x inside the region, or the determinant is strictly bigger than 0 almost everywhere in omega. Right? And this just followed from the story of decomposition. So this is U, this is a G, and this is a phi. And the moral was that if we had a set of positive measure, which we called B, such that the determinant was equal to 0 in B, then the image of B in G of omega would have positive measure. So this would be the bad set B. The image would have positive measure. And then the gradient of phi on this set of positive measure would have to be 0 almost everywhere, and therefore would have a cluster point inside this region, and therefore phi would have to be identically equal to 0. Yeah? Cool. So we are going to apply this to the 3 gradient problem. So, theorem. Suppose we have a set of matrices contained in 2 by 2. K has no anchor connections. If we have a mapping U such the gradient belongs to this set almost everywhere, so it's going to be Lipschitz if that's true. Then actually the mapping is affine, and the gradient is just one of these fixed guys. I should also say this is connected. Okay. Proof. So I asked you guys to think about it. Yeah, if it's affine, then gradient's constant, so it has to be equal to one of these guys almost everywhere. Okay, so why is this the case? So we're going to make a reduction. We're going to reduce this to the set of matrices 0, and then one of these guys minus the other, and then the same guy minus the other. Hard to express. So we're going to pick one guy, one of these A1, A2, A3, and subtract it from the others, okay? And deal with 0 and those other two, okay? And the advantage of that being will be, hopefully we can apply this theorem, because if we have a set of positive measure for which the gradient takes the 0 guy, if we happen to get a quasi-regular mapping, then that set is the entire thing. Yeah? That's the strategy. Yeah? So, notice the following. So, we can do it this way. So, if determinant of, say, AI minus aj is positive, then since these are 2 by 2 matrices, that's the same as the determinant of aj minus ai, right? Yeah. So let's draw a picture. This is A1, this is A2, and this is A3. And between any two of these guys, there is either a positive relation in the sense of determinant of the difference is positive, or there's negative relation in the sense that the determinant of the difference is negative. And it doesn't matter which way around we order them. So it's just about the choice of pair, right? So we can consider this as a graph, and the edges are like this, and each edge has a sign. The sign is either positive or negative, right? So we're going to put a positive sign if the determinant of the difference is positive, and a negative sign if not. So create this graph. The edge given by ai aj is positive if and only if determinant of ai minus aj is positive, and negative if and only if determinant of ai minus aj is negative. So on this graph, we can label it positive, negative, depending on the edges. I mean, so for each edge, we have a sign we put on. Yeah. So let's do some arrangement. For example, positive, positive, negative. Yeah. Or it could be negative, negative, positive, or anything like this. Yeah. But what has to happen is that we must have one of these edges. So again, one of these vertices of the graph having two edges of the same sign. That has to be the case. Yeah? Because the edges are either positive or negative. There are three of them. So at least two of them have to be the same sign. Thumbs up if you agree. Yeah? So if we have two edges that are positive, like this one, then we can do the following thing. So let me write that down. There are three edges. At least two of the same sign. If let's actually label like this. So if we have that for I1, I2, I3 belonging to 1, 2, 3, we have that determinant of aik minus ai1 is bigger than 0 for k equals 1, 2. No, k equals 2, 3. So this is I1. This would be I2 and I3 like this. Then, running out of space a bit here. Then let w of x be u of x minus ai of x, or ai1 of x. Yeah? So therefore the gradient of w belongs either to 0, ai2 minus ai1, AI3 minus AI1. Yeah? All right, tell me why we're very happy with that. It might be equal to 0 on a set of positive measure. And then what happens then? Okay, so is W quasi-regular? Why? And why is that true? We can have any K that we like, right? Why is this true? Can anybody help? U is Lipschitz, yeah, but this isn't a property about I mean, U is Lipschitz just from the fact there's differential inclusion into this finite set. This is a property of this finite set of matrices, huh? So we have three possibilities for the gradient of W. Either the gradient of W is in 0, yeah? Does the 0 matrix satisfy this for some K? Does the 0 matrix satisfy this? Yes, it does, right? Yeah, yes, it does. Both sides are 0. Or it's this matrix here. Yeah? Does this matrix satisfy this for some K? Come on, people. So what's good about this thing? The determinant of this thing is positive, right? It's not 0, it's positive. Yeah? That's how we built this construction. Yeah? So the right-hand side will be positive, right? The left-hand side is just the operator norm of this thing, which is just some number, right? No matter what these matrices are, this is just some number. It could be 100 million trillion, we don't care, it's a number, yeah? It could be that the operator norm of this is 100 million trillion and the determinant is 0.0001. We don't care, because it's still some constant k, such that the operator norm squared is bounded by k times the determinant. Yeah? Cool. And the same is true of this. The determinant of this thing is positive. Could be very, very small, but it's positive. The operator norm could be absolutely huge. Again, we don't care. There's still some constant k for which that's true for this matrix. Yeah? So we just take the max of those two constants k, and then for every gradient inside this collection of three gradients, then this will be true. You will see what I mean. Thumbs up if yes. Yeah. It's not independent on your choice of these guys, but no matter which one we choose, there is still some constant k. So let's write it out. So note. For some k1, we have that the operator norm of AI2 minus AI1 squared is less than equal to K1 determinant of AI2 minus AI1, like this. Because this thing is definitely positive, whatever this is, we just could find some constant for which that's true. Yeah? And there's another constant such that this is true. AI3 minus AI1 operator norm squared is less than K2. Determinant of AI3 minus AI1, yeah? So then just take K to be the maximum of K1 and K2. That for that K, this is true for every gradient inside this list of 3. Okay, thank you for this question. Cool, so W is definitely a quasi-regular mapping, yeah? K quasi-regular. So if we have the set of measure for which the gradient of W hits 0 as positive measure, then it must be the entire thing, right? So omega take the set of x such that dW equals 0 is 0, yeah? So now we reduce the situation to a, well, we either have that the gradient's entirely inside this guy, which corresponds to W having its gradient entirely inside A1, or we have that this has got a set of 0 measure, and the gradient never takes this, the gradient of W never takes 0, or almost never takes 0, and therefore U almost never takes A1. So we reduce the problem of 3 gradients to the problem of 2 gradients, as Hyogo said. Everybody with me here? Yeah. So if we couldn't find this, and there's no reason why they have to be positive, they could be negative. So let's say we had this, for example. Then we would just multiply things with a matrix to flip the sign, and we would all be good. So let's put that here. Actually, maybe I just erase and put it on a new board. Just like, if we can only find I1, I2, I3, 1, 2, 3, such that the determinant of AIK minus AI1 is less than 0 for K is equal to 1, K equals 2, 3. Like this, then let's multiply on the left-hand side by this matrix. Let's call it B is minus 1, 0, 0, 1, right? So B has got determinant minus 1. So let's V of x be I'm identifying the affine mapping with gradient B as B itself, as B of U of x, right? So then gradient of V of x equals B of gradient of this, and now we have all the stuff is all the determinants are flipped. Right? So determinant of A, I, K, determinant of B aik minus b ai1 is determinant of b determinant of aik minus ai1, which is bigger than 0 for k is equal to 1, equals 2, 3, right? So then this guy, v, is in the situation we were in before. We have that the gradient of v belongs to either 0, no, not this way. So we have to maybe define w again by subtracting this. So w of x be v of x minus b ai1 of x, like this, yeah? Same procedure. And then gradient of w of x belongs to 0, and then b of ai2 minus ai1, b of ai3 minus ai1. Yeah? And again, w will be a quasi-regular mapping, and if it takes on a set of positive measure this 0, which is the same as u taking a I, then it has to take it everywhere, or almost everywhere. So in either case, we reduce it down to just having two matrices. Yeah? So reduces to the case of Lipschitz U with du belonging to a set of two matrices, let's call them M1 and M2, with no rank connections. Yeah? Cool. And then you can see how we're going to argue. So then, in this case, if determinant of the difference, say M2 minus M1, is positive, then again we define W of x to be U of x minus M1 of x. W is quasi-regular. It's either going to take one or the other. Yeah? Yeah? So if it takes the zero matrix on a set of positive measure, it takes it everywhere, so it must take it on a set of zero measure, therefore it takes this guy everywhere. Yeah? And then if we have that this is negative, then we're going to multiply on the left-hand side by b again. We're going to have a quasi-regular mapping, and then apply it. And then what is true for the quasi-regular mapping is true of original mapping because we just multiplied it by an affine mapping. Cool. Everybody happy? Everybody clear? Yeah? So this completes the proof. Right? So in the case minus M1, oops, it's 0 multiplied by B. Okay, that's so. This can be proven without the theory of quasi-regular mappings. It's just a neat application of some of the power of this theory that we can actually establish this. What, as far as I know, can't be proven without the theory of quasi-regular mappings is the 4 matrix case. So this is a theorem by Lebesgue and Geheim. I'm not sure how many H's. Go ahead. No, no. Well, I mean, there are definitely common ideas in the proof of the four matrix theorem. But what I was saying was that we need to use the theory of quasiregular mappings in an essential way. So it's possible to prove this result for three matrices without using quasiregular mappings. You can just argue by hand and be quite careful in your sequence of steps. But for four matrices, as far as I know, and I'm pretty sure that this is true, there isn't a proof which doesn't use the theory of quasiregular mappings. It's an essential part of the proof. And there's only one proof of this result, and it's by Lebesgue and Geheim. And this is from around, I guess 2003 maybe. No, earlier, I'd say 2000. I think it was proven even before 2000. And this is their theorem. So suppose we have a set K. So you can do this in any dimensions, but you can reduce it to 2 by 2 without too much problem. So suppose we have K, which is consisting of sets A1, A2, A3, and A4. No R1 connections. If the gradient belongs to K almost everywhere, omega, which is connected, then U is affine. And therefore the gradient is just one of these guys. This paper is pretty short. It's about 10 pages, but it's very concise. So I'm thinking about what to do next week, and I might give you a sketch of this thing if I can come up with a sketch that's not too technical. That gives the main ideas without going too much into details. So I'm still thinking about if I can present this. But this is in contrast to another theorem around the same time, which says that 4 is as high as it goes. And this is by Geheim and Price. Price was my former PhD advisor way back in the day. Let me say it this way, there exists a set of 5 matrices, and you can take them in 2 by 2. I think they can also be symmetric. U belongs to K almost everywhere. K has no connections. And U is non-affine. So it's a non-trivial mapping. In fact, it's highly non-trivial. You can have a function which has its gradient inside this set of 5 non-rank 1 connected matrices, and it's non-affine. In fact, it's very wild. The gradient of this guy cannot be a measure. So it's the set of interfaces where it jumps from one of these guys to the other it's got infinite measure. I'm aware you can't really understand what that means, but just to give you some words about this, these are not easy to construct. There's no way to do this in just one step because there's no way to begin. You can't begin to layer in these matrices A1 and A2, A3, A4, A5. There's no rank 1 connections between them. So it's a highly non-trivial thing to establish this, but nevertheless it is true. And this is using a method called convex integration. And this is related to the Tata square that I showed you previously, that we could kill compactness with this example of 4 matrices with no rank 1 connections by creating these functions that take the gradient inside this set of 4 on a very large set. On a small subset, you have these errors. There's a way to gradually replace those errors by things inside the set you're trying to force the gradient to be inside. And its origins is from some concept of Gromov. I think he coined the name convex integration. The very most origin of this is these embedding problems solved by Nash of embedding some manifold inside a higher dimensional Euclidean space. And to do this, he developed this kind of an iteration scheme, and at the very beginning, the very origin of this concept of convex integration, and it was pushed, and eventually reached calculus variations, was applied to these kind of problems, and then later has been applied very successfully to counterexample many questions or many other problems in PDEs, as we talked about a little bit last time. So these are quite opposite directions. This is using theory of quasi-regular mappings to show that there is rigidity, that you can only have trivial things. And then here it says that there's a threshold where if you have 5, then you have highly non-trivial things. And it's a very beautiful result to fully understand this. This is one of those elementary results that our mathematical ancestors would have appreciated and seen the point of. But again, this is with relatively recent methods. Okay, so let me clean the board. My final 10 minutes, so I will talk a little bit about convex integrations, applications to PDE, and then we'll wrap it up. Applications of differential inclusions. PDE. Definitely not these. Okay. So, recall the Euler Lagrange equation we got from this minimization of a vector-valued function of an energy of this form. There's the divergence of the gradient of f of gradient of u equals 0. The gradient of f, so f is some energy from space of matrices, let's do 2 by 2 as always, into R. So the gradient will be something from 2 by 2 into 2 by 2, and therefore divergence means the divergence of each row. So this is a vector equation. This is a system of equations here. Yeah? So, as I was saying last time, it was an open problem for a long time, whether or not for weak solutions of this, so I write it like this in the distributional sense, do these weak solutions have partial regularity in the sense that their gradient is smooth on an open set of full measure, because that was proved if there are local minimizers of this functional. So if you just have the PDE itself, just have the Euler Lagrange equation, is that true? And the answer turned out to be no. And this was turned into a differential inclusion, and some of these wild solutions that I was just talking about were necessary to produce a function whose gradient only takes 5 matrices without random connections. So these wild solutions were created to solve this differential inclusion. So let's see how we can turn this into a differential inclusion. So let's, for notational simplicity, let g of x be this thing, df of x for x inside 2 by 2. So g is just a function from the matrices to the matrices, yeah? And then consider the following set. So let J be this matrix 0, minus 1, 1, 0, like this, and then consider the following set of matrices, set of x, and then g, x, j, like this, for x, which is in 2 by 2. Okay, so this is a set which is 2 by 2, and then another 2 by 2 underneath, right? So it's going to have 4 rows and 2 columns. Yeah. Yeah. And actually, let's call that something. Let's call that K. Then, if we have some function, say gradient of w, belonging to K almost everywhere, where w is a function from R2 to R4, right? Then what would that mean? That would mean that, put it over here, that we have, I don't know if I want to write the entire gradient, so maybe I have to. So we're going to have W1, 1, W1, 2, W2, 1, W2, 2, W3, 1, W3, 2, W4, 1, W4, 2 belongs to this set K like this. So, yeah, let's write it like this, belongs to K. So, what does that mean? So if you look at this bottom half of this 4 by 2 matrix, this thing here is the gradient of a function from R2 to R2 if we just consider the final two coordinates of W, W3 and W4. Yeah? So in particular, I am losing my ability to be articulate. In particular, that means that if we consider the curl of the bottom 2 rows of this matrix, that curl will have to be equal to 0 because the bottom 2 points of that matrix are gradients. I think I just totally didn't explain that well. All right, give me a second. So suppose this belongs to K almost everywhere. Well, what does that mean? That means that we actually have that gradient of W will be equal to something inside this set, right? And the first 2 by 2 matrix of this 4 by 2 matrix will be given by this thing right here, yeah? And so that means that this thing will be of this form. It'll be W1, 1, W1, 2, W2, 1, W2, 2. And then it'll be this G of this thing here. And I don't want to write it all again, so let's put this matrix like this, times this. Yeah? Yeah, that'll be what the gradient has to be. Yeah? But that means that the bottom two rows of this matrix are these things right here. Yeah? So if we let U x1 or U of x be just the vector value function W1 of x, W2 of x, like this, yeah? Then we can express it like this, that gradient W of x is equal to the gradient U of x, this 2 by 2 matrix, and then G of the gradient U of x times J, like this. Yeah? Cool. So, this implies that this stuff right here, if we let V be the bottom two coordinates, say W3, W4, then this stuff right here means that G of this is this gradient like this almost everywhere. Yeah? Okay. So in a weak sense, that means that the curl of each row of this guy is equal to 0 because this is the gradient of something, right? So its curl is 0. So curl of G of this, I'm not going to write x anymore. In the weak sense, yeah? But what is curl? Curl is minus the x2 plus d by dx1, right? That's curl. Yeah? But we're multiplying on the left-hand side by this j, and this j is flipping the order of these elements. So what I mean is, if we look at this thing, so if we have a matrix like this, A, B, C, D, and then we multiply it by J, what happens, then we are going to get minus B, taking this guy and this guy, and then we're going to have A, and then we're going to have minus D, and then we're going to have C. Whoops, this was A. And this is C. Yeah? So, if we have curl applied to this matrix here that we've flipped around with this J, right? That would be the same as applying just the divergence to G of the gradient itself. Right? Because what does this matrix do? It just flips the elements of the top row and puts a minus, right? It exactly flips them around. Yeah? So curl of something like that is the same as divergence of not doing that. You see what I mean? Yeah? So then, this is the same as insisting that the divergence of G of this thing is equal to 0 in... yes, but it's 0, so the minus we don't care about. Yeah? And then that's exactly the Euler Lagrange equation that we were trying to solve. So the issue is, if we can construct a non-trivial differential inclusion into this set of matrices K, and that's just a set of matrices, right? It just depends on the G here. And we run over all 2 by 2 matrices, and we have this 4-dimensional subspace inside this 8-dimensional space of M2, M4 by 2. Yeah? So if we can create a differential inclusion onto this 4-dimensional submanifold, where the gradients are non-trivial, they're jumping from one to the other, the way we can with these limited type constructions. If we can do that such that the gradients are jumping on almost everywhere, then that would kill any higher regularity of the gradient, right? That would prevent us having higher regularity, because the partial regularity statement of Evans was that on a set of full measure, an open set of full measure, the gradient is actually continuous. It's smooth, even depending on how smooth f is. Yeah? And the point is that if we can construct functions whose gradient jumps around a lot with these limited constructions and build them inside this differential inclusion, then we will be in good shape. We'll count, for example, this conjecture that this equation by itself has regularity. And that's what they ultimately did. But the caveat is that if you have a quasi-convex functional f, or strongly quasi-convex functional f that is in the initial posing of the problem, then this set doesn't have rank 1 connections. Okay? So you are stuck with the question of building non-trivial differential inclusions into a set without rank 1 connections. So if f is strongly quasi-convex, then K has no rank 1 connections. So this convex integration method to build differential inclusions into sets without rank 1 connections comes into play, and that's how ultimately Muller and Sverek were able to solve this problem. So this was a whole kind of like a minor sort of tidal wave of results that came from learning this convex integration techniques from Gromov and applying them to calculus variations, applying them to classical differential inclusions. Solved a lot of questions around 2000. And then it was pushed further and further and further into nonlinear PDEs, and is, as I said, one of the hottest things around. Okay, so that's all I have to talk about today. No. All right, so I'll see you all on Monday. Have a great weekend. Bye-bye.